Hello friends, welcome to the next lecture of RSA algorithm. Here, this is also considered as a public key crypto system algorithm. The algorithm of RSA was invented by Rivest, Shamir and Adleman of MIT in the year 1977, and therefore it is termed as RSA by taking the initials of the three scientists who discovered it. It is a best known and the widely used public key scheme. It is based on exponentiation in a finite field over the integer modulo of a prime number. We'll see in details how this exponentiation works and how the prime of a modulo number takes place. Exponentiation takes place for that is the O of log n to the power of 3, and this operations only makes the difficulty to the attackers. It uses large integers, example that is of 1024 bits, because then it also requires the modulus operators, modulus operations, and thus it increases the security. Security due to cost of factoring large numbers. Here we need to factor the large number, factorization of large numbers needed here, and therefore it requires mathematical computations, and which enhances the security of RSA algorithm. Factorization takes place as O of E log n operations, which becomes then difficult for the attackers to find out the keys. Now let us begin with how the RSA encryption and decryption takes place. So to encrypt a message, plain text message M, the sender has to obtain the public key of the recipient, for which we have to compute to find the value of N, which then gives you PU. PU is the public key of the recipient, which is nothing but a pair of E and N, which then helps us to compute the value of the ciphertext, which is computed by using the formula C is equals to M to the power of E mod of N, where 0 less than equal to capital M less than equal to N. Here capital M is nothing but your plain text message. Then to decipher the ciphertext, that is to decrypt the ciphertext, we have to use the following formula, which is M is equals to C to the power of D mod of N, which then gives you the plain text back. And for this we have to make use of the private key, which is nothing but a pair of D, N. One thing is to be noted that the message M must be smaller than the modulus N. This is the step-by-step setup for the RSA algorithm. It generates a public-private key pair by selecting two large prime numbers, and these two large prime numbers are random prime numbers. Here we consider these two prime numbers as P and Q. Then the next step is to find the product of P and Q, that is N. And then to find the value of phi of N, we just have to take the difference of each, that is P minus 1 multiplication to Q minus 1, will give you the value of phi of N, which will then help you to find the encryption key E. So selecting any random encryption key E, we should have consider one condition, that is 1 is less than E should be less than the value of phi of N, which we have computed from the above step, and that is nothing but the DCD of E and phi of N should be equals to 1. Then we have to solve the following equations to find the decryption key D, wherein we have to solve E into D is 1 mod of phi of n, which should satisfy the condition of 0 less than D less than n. Out of these computed steps, we will be then getting the public key and the private key pairs, which are PU, a pair of EN, and PR, a pair of DN. Why the RSA works to increase the security? Because of the Euler's theorem. You all must have learned this Euler's theorem in your mathematics, first year mathematics or the second year mathematics, which gives you the GCD of A of n as 1 and a to the power of phi of n mod of 1, n is 1. And in RSA we have the n, which is the product of p and q, and phi of n, which is the product of p minus 1 and the q minus 1. Here we have to carefully choose the values of E and D to be inverse mod of phi of n. And hence we can then find the value of E dot D is equals to 1 plus k phi of n for some values of k. And hence we can then find the ciphertext and the plain text. To find the ciphertext, we have to compute this formula: c to the power of d m to the power of phi of n to the power of k, which is then giving you the final computed formula as c to the power of d m mod n. Let's take an example of RSA algorithm where we have just selected any two random prime numbers, that is p as 17 and q as 11. When with the help of p and q, then we calculate the value of phi of n and the value of n, which are the most important two values to get your private and the public key. Here, once we get the values of n as 187 and the value of phi of n is 160, we then have to select such a value of E so that the GCD of E and phi of n should equals to 1. And then once we get the value of E, we have to determine the value of D, which is nothing but DE is equals to 1 mod of 160. After calculating, we then get the values of D as 23, and hence we get the private key PR as 23,187, which is nothing but D, N, and the public key pair as 7,187, which is nothing but E, 187. We will see in detail how to choose the values of E and then how to determine the values of D once we start with the numericals part. This was just an example to tell you how the things are computed in the RSA algorithm. RSA encryption and decryption. Encryption gives the ciphertext of your plain text message. So here your plain text is, if we consider the plain text message M as a numeric value of 88, so the encryption would then give you the value of 88 as 11. That means we then have to compute all the steps which we have seen just now for converting your plain text to ciphertext. And if we take the equation of ciphertext to find the value of ciphertext, which then gives you m to the power of e mod of n, that is 88 to the power of e, that is 7 mod of n is 187, which then gives you the value as 11. Similarly, to find the decryption, we have the formula of m is equals to c to the power of d mod of n, which then gives you back your plain text, that is the value of plain text, which is 88. Thus, the encryption and the decryption part of RSA algorithm is solved. The exponentiation, this can use the square and multiply algorithm. It is as fast and efficient algorithm we have to use for the exponentiation part. Concept is based on repeatedly squaring the base and multiplying in the ones that are needed to compute the results. Also, it looks at the binary representations of the exponents. Only it takes log of O log of n to the base 2, which multiplies for number n. And this multiply of number of n in this exponentiation part only increases the security of the RSA algorithm. So in this way, we have to just factorize, we have to just find the exponentiation part for the RSA algorithm. Now, how to define the efficiency of the encryption process? Encryption uses the exponentiation part to the power of e. E is considered as one of the pair of the encryption key. Hence, if e is small, this will be faster. That means if the value of e is to be considered as a small, the RSA algorithm would work faster. And often e is chosen as the power of 2 to the power of 16 minus 1. Also, there are some choices of e which needs to be taken care of. That is, e can be considered as 3 or 17, whichever the lower value of e is considered, it will then fasten your encryption process. But if e is too small, then attacker can easily get the idea of the public key, and then the messages with the different modulos can be then tried to get the values of the key. If e is fixed, must ensure the GCD of phi and e should be equal to 1. That is, reject any pair or q not relatively prime to e. We have to take these considerations very well to give the efficiency to the encryption of the RSA algorithm. How to efficiently decrypt the message? Decryption uses the exponentiation to the power of d. This is slightly large and secure if not. Can use the Chinese remainder theorem to compute modulus p operations for the decryption process and the q separately. Then combine, you can get the desired answer of the decryption process, which will then gives you the plain text back. Approximately, it is 4 times faster than doing directly. Here, as the owner only knows the private keys, and he is the one who only knows the values of p and q, can use this technique, and then with the help of the Chinese remainder theorem, the receiver can easily decrypt the message and can get the plain text back. How the keys are generated? Users of RSA must determine the two primes at random, that is p and q. Then by selecting the values of e or d is computed. Primes p and q must not be easily derived from the modulus n is equals to pq. In such a way, we have to find the values of p and q. That means we have to find the values of two prime numbers which are relatively prime to each other. Also, typically it shouldn't guess and shouldn't use a probabilistic test to get the values of p and q. Exponents ed are inverses, so use inverse algorithm to compute the other keys. That means we have to use the inverse key algorithms to compute the other key values, which are then used for encryption and decryption process of the RSA algorithm. How the RSA security is defined? Possible approaches of attacking RSA are the brute force key search, which we have already seen how the brute force works. Different types of the mathematical attacks can also be possible depending upon the difficulty of computing phi of n by factoring the modulus n. There are another type of attacks which can happen, and they are the timing attacks, which runs on the decryption process. Also, chosen ciphertext attacks are there given the properties of RSAs. Here, which increases a factor which increases the security of the RSA is the factoring problem. The mathematical approach takes three forms, where we have to factor n, where we have to find the values of n, that is a factor n, p mod combination of P and Q, and then we have to find the values of phi of n, and then D. For this, we have to determine the phi of n directly and compute the D, find D directly. These are the mathematical approaches in three forms, which then sometimes can create a problem of the factorization. Currently believe all equivalent to factoring. This have seen slow improvements over the years. Biggest improvements comes from the improved algorithms. Currently, it can assume that 1024 to 2048-bit RSA is secure, wherein we have to ensure that P and Q of smaller size, that is the two prime numbers are of the smaller size, and matching the other constraints of the RSA algorithm for the factoring problems for the encryption and decryption process. This is the progress in factorization, we can say. With respect to the number of decimal digits, approximation of number of bits, data achieved, MIPS years, and the algorithms. So for the number of digits, decimal digits, like if we take the example of 130 decimal digits, then what will be the approximate number of bits needed is 431 bits. Then how the data is achieved, in what year that particular data is achieved, and the algorithm which then helps in progressing the factorization or factoring problem which was faced by the RSA algorithm. This is just the graphical representation of the progress in factoring, wherein we can see that the MIPS years needed to factor versus the bits which are then needed to factor, and which then gives you the progress in factorizations. These are some of the timing attacks which can happen on the RSA, which was developed by Paul Kocher in the mid-1990s. Exploits the timing variations in operations like multiplying by small and large numbers or varying each instruction's execution. RSA also exploits time taken in the exponentiation part for its mathematical computations. The different countermeasures like use constant exponentiation time, adding the random delays, the blind values used in calculations, and so on. These can be considered as the different factors which can be used for the type of the attacks on the RSA algorithm. Chosen ciphertext attacks are like we have to choose a ciphertext, that is CCA, for which the RSA is vulnerable to, wherein the attackers chooses ciphertext and gets decrypted plaintext back. Chooses ciphertext to exploit the property of the RSA to provide info to help the cryptanalysis type of the attacks, because cryptanalysis type of the attacks can counter with a random pad of the plaintext or the optimal asymmetric encryption padding, which is called as OASP. This is just a diagrammatic representation of OASP, which is nothing but optimal asymmetric encryption padding, wherein we can see that how the encoding parameters are used, how the message is to be encoded, how the hash function is then used on the encoding parameters, how the padding is then used, and after the implementation of the padding here, the data blocks are created, and then those data blocks undergo the MGF function, that is the mask generating function, which then XORed and masked your database block or data block, and then at the end of all these steps we get the encoded message. So this is the optimal asymmetric encryption padding. Actually, these things are not clearly mentioned in your syllabus, which has to be covered, but as the extra knowledge to you all, I've covered all these topics under the RSA. In your syllabus, only the RSA algorithm, the basic functionality of RSA algorithm and its numericals are included. I just hope that you might have got this concept of RSA very surely. Thank you.